Mr. Grant, you're now the host and we're live on YouTube.
Okay, thank you.
I don't know, you're muted. You're muted, so I'm not hearing you if you're speaking.
I was saying, okay, thank you. Can you hear me now?
Oh, you're welcome.
Good afternoon, my physics students. Thank you for joining me today on this physics journey. We're going to take a roll through some physics CSEC past papers, and by doing this, the things that we can find out our strengths and we can find out our weaknesses, but most definitely, it will help us to be better prepared. I can recall this text in the Bible that says the prudent man, and another word for prudent is the wise man or the man that is prepared, right? See the evil, the destruction coming from afar, and he hide it himself. But those who go on and ignore it, they are taken away as fools. So we want to be prepared for what is coming because we are wise and we are prudent, and we're going to take this time now to do that. All right. Let us begin by bringing up a few papers. Hold a minute. Here we go. So we have wonderful opportunities here to take a look at. And I definitely do want us to take a look. Hold on a minute. Okay, here we go. Now we're going to start out with these questions. This is from the 2010 paper 1 physics exam, CSEC. And we start off with the question that we see right here. Which of the following groups of quantities contain one which is not a SI-based quantity? And if you know anything about the SI aka base quantity, that's the same thing as saying the fundamental quantity, which means it is not derived. It is one of the original quantities for measuring different physical characteristics in this world of energy and forces and matter and all of this kind of stuff. So the actual answer here is this one with volume. Volume is a derived quantity by combining different dimensions of length, right? So that is the one that does not have all SI-based quantities. Question number 2 says 3.141596. And if you should be familiar with this, you'd probably recognize that this is the number for pi, that little curly thing associated with calculating measurements for circles. And they're asking to express this to two significant figures. Now, if you remember anything about significant figures, the zeros are not significant unless they're held between two other non-zero digits, right? So it doesn't matter where the decimal point is. You start coming with the first non-zero number, and that number is 3. So we have 3, and if I draw for my just a pen, so this 3 here is going to be our first digit, and that 1 there also circle is going to be our second digit. So they said two significant figures. But guess what? We always want to check the third one to see if we're going to go up or remain. All right. And the third one is going to be the 4 here. And if it is 5 or more, we round up by 1. We round up that second figure by 1. But if it is not 5, it is less than 5, we're just gonna drop them. And so the answer must be 4.1, 3.1, my bad. And this is our answer right here. All right, for this one, we had said that this one is the odd one out. All right, here we go again. The symbol for the unit of moment of a force is moment of a force. Now, please remember that moment of a force has to do with the turning effect of a force. And if I could just put a simple diagram on the screen right here, I'm going to put up a seesaw. You guys know seesaw? Of course you do. You have been a child at some point in your life. So here's our pivot right there. I'm just going to put that there, and I'm going to tell you that, let's say there is some body right here and the weight acting down right here. So this weight here is the force, and this distance between the pivot and the objective force or weight is going to be called D. So the formula for this is moment of a force, and I'm just going to call it MOM, mom. You know about moms. Moms can be really forceful and get you into all sorts of direction, get you moving. F times D, and we know that force is measured in newtons and distance is measured in meters, so it is Newton meter. Where do we find that? That answer is, of course, question B. So there we have it, question B. All right, let's go again. That was number 4. No, sorry, number 3. And so we're going to go to number 4 right now. Here we go now. And we're off to number 4. And this one says, the unit of electrical resistance is expressed as... All right, so what do we know about the unit of electrical resistance? What do we know about it? All right, so at this moment, you should be saying Ohm's law. You should be stating Ohm's law right now. And Ohm's law simply states that the current, you know, that the moving charges, you know, in a conductor, the current I is directly proportional to the voltage, which is the difference in potential or the force that drives the current, you know, right? And is inversely proportional to the resistance. That is basically that property of the material that tries to resist the charges moving through it, right? And this formula, it actually turns out I could just drop out this proportionality sign and actually just put the equal sign, and it works. And this is Ohm's law says that, yes, so the current. So if we take a note of this, this is the formula. And in this, they're asking us for the unit of resistance, which means that we want R to be by itself. So what we're going to be doing is we're going to carry R over on this side to multiply to get it from the denominator at the bottom of the fraction, which is going to give us V equal IR, right? And then now to get R by itself, we need to move the I to over here, and it's going to divide. So the resistance is going to be voltage over current, all right? Voltage over current. And if that is the case, voltage is measured in volts V and current is measured in ampere. So it is volts per ampere. Where do we find that? Volts per ampere, it's right here, the very first one, 1 volt times the division of 1 ampere. All right, and we All right. So there we go. That's that for that one. So this is now number 5. Number 5, it says the time period of a simple pendulum. Time period of a simple pendulum oscillating with small amplitude depends on the. Okay, so if you're wondering what is this simple pendulum? So I got this little ring right there, and to it is tied a string, and on that string is a bob. A bob is just some kind of dense mass with a weight, W, which is affected by gravity, of course. And the length L that they speak about is the length of the string from where it is tied there to the center of the bob, like that. And that's L, measured L. Now, what we notice is that no matter how wide or how hard you swing this, the acceleration for it to go back, to go forward, go back to the other side and come right back to starting point is going to be the same amount of time no matter how hard or how small, how lightly or how greatly you push the bob. But we notice that if you change the length of the string though, whoa, great effect happens, right? And so the thing is, the answer is going to be the length of the pendulum. This is what really changes the time. The time is affected by how you change the length. And that's something that maybe we can look into a little bit more in later time. All right. All right, let's take another look again. All right, so here we are. We're at question number 6. Now, 3 immiscible liquids, P, Q, and R, have different densities. Q is denser than P, but less dense than R. Which of the following diagram shows the liquids settle in the measuring cylinder? Now, please remember that more dense, let me first explain density. So remember that density is a component of the structure of the material to say how much mass of the material is stuffed into how much space. So the more mass you stuff into a small space, the more dense the material is, and it's said to have a heavier effect. And the more spread out the mass is, right, the less dense the material is, and it tends to have a lighter effect. Examples of this lighter effect, you may ask things like paper, styrofoam, styrofoam, right? Plastics, wood like bamboo. The denser effects like concrete, stones, metals, more the heavier metals that is, because you do have light metals, but yeah, most of the heavier metals like lead, gold, silver, copper, iron, those heavier metals, they tend to be dense, right? So, and they have this phrase like they like to say, as heavy as lead. Lead is, of course, a metal, and it's one of the densest metals out there. So as they like to use the phrase as heavy as lead. All right, so what will happen now is that the substance with the heavier effect, which is the one that is more dense, is going to sink below the ones that is less dense than it. So less dense floats above that which is more dense. That with the lighter effect will go on top of the one that has the heavier effect. But that already made sense to you. So we take a look. So P, Q, and R, right, have different. Q is denser than P. So the fact that Q is denser than P means that Q must be below P. Right? So anyone with Q at the top is out. All right, so Q must be below P. But P is less dense than R. But P is less dense than R. So Q must be below P. Right? And P must be above R. All right, so Q below P, all of those with Q below P. A and D. Right? But then it says that P is less dense than R. Of course. Yes, so P must be above R. All right. And as we can clearly see, he will demonstrate that. All right, let's take some more. Let's take some more look at what is going on. A bus with luggage loaded on top is more likely to tip over when rounding corner than the same bus without the luggage. The reason for this is that the luggage, all right. So this has to do with stability. All right, and let me tell you the ideas for stability. The lower the center of gravity, so let's say I have this block here, right? If the center of gravity can be at 1, 2, and 3, the lower the center of gravity is, the more stable it is, meaning that the less likely for the thing to turn over. It's harder for it to turn over when it's more stable. When it's less stable, it's easier for it to topple over on its side or top, you know, depending on the shape and all of that. All right, so that's 1. So the lower the center of gravity is 1. Now, the wider the base, right? So wider the base. All right, so let me take a look now. So we have the base can be this width. The base can be this wide. And the base can be as wide as the extreme. Now, you see the one with the widest base is going to be more stable because the moment to be overcome to cause this thing to topple over on its side is going to be far great in comparison to the width. So here we go. So here we have it right here. The wider the base, the more stable. The next one is you want the base in effect to be wider than, you want the base to be wider than the top. So the greater the ratio of the base, the width of the base compared to the top, is also the more stable that is. All right, so these are the 3 principles. Now, as it relates to the luggage, when you put the luggage on top of the bus, the center of, because the weight is on top, the center of gravity is going to go higher and cause it to be less stable. So that's what this violates, because the shape of the bus don't really change with the luggage, but the distribution of the mass does, which will cause the center of gravity to shift. So the center of gravity shifts from being lower, where most of the weight in terms of the chassis and the engine and the wheels and so on was at the bottom. When you put those luggages on the top, there's some weight at the top, so the center of gravity have to average between the 2 set of weights, and it goes up higher. And that raise in the center of gravity makes it easier for it to turn over when you're going around corners. All right? All right, so here we go again. All right, so we're at number 8. It says in figure 8, refers to the following diagram that we're seeing right here. And this, of course, is a diagram of momentous proportions. I'm sorry. It is about moments. It's about, turning effects of forces, right? And here we go now. So it says, a uniform rod XY of weight 40 Newton is held in equilibrium. Now, you're probably wondering, why is it that you're telling that the rod is uniform? Does it mean that it has on clothes that is like everybody else and is a standard wearing garment for all the rods? No, in this case, when they're using the word uniform, it's talking about consistency. That means it's consistently, the weight is consistently or evenly distributed throughout. The thing about wearing uniform, as you wear uniform practical, is that everybody has on the same thing. So there is a sense of commonness or consistency or constancy about everybody that has on the uniform. So as it relates to the rod now, they're saying the weight is evenly distributed all about the rod. Right? So that there's no unevenness about it. There's no unevenness about it. So that being said, the weight of this rod is going to be, the center of gravity for this rod is going to be in the center since it has evenly distributed weight. If it was unevenly distributed, then there would have to be some calculation or measurement about that. But in this particular scenario, we don't have to do that. It's uniform. Now that it's uniform and the rod of weight 40 newtons, please remember as it talks about weight being 40 newtons, there's something I must say. Remember that weight is mass times the acceleration due to gravity, coming from Newton's second law, which says that force is equal to mass times acceleration. All right. So that means the acceleration is based on the size of the force, or the size of the force and the acceleration are directly proportional. And of course, the mass does have a lot of part to play in that. Anyway, so this when they say the weight right here, that's the force due to gravity, and that is the mass times the acceleration g due to gravity, is held in equilibrium. Now, you have to know the conditions of equilibrium. When we talk about the conditions of equilibrium, this is simply saying that all the forces that are going upward must balance all the forces going downward. And all the forces going eastward must exactly balance with all the forces going westward, so that there is no movement or motion. And we have a state of what we call balance. Another thing to say is that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments about the same point. About the same point. About the same point. All right? All right, so let's take a look. So here we go. And they correctly put in the 40 Newton right in the center there, where the center of gravity would act for a uniform rod. And then they're going to show you that there's a tension force T2 here and a tension force T1 here, both of them pulling upward. So those are the different upward forces. Now, of course, we can tell that the sum of the upward forces must be equal to the sum of the downward forces. Yeah, we know that. So we know that T1 plus T2 must add up to 50 Newton, since 50 Newton is the sum of the downward forces. But that don't tell us which one is bigger than which one. So let's get into this. So let's say which one of these is true. All right, so let's take a look at the sum of the clockwise moments being equal to the sum of the anti-clockwise moments about the same point. So there are multiple points that we can do it from, and we're gonna do it through the center of gravity right here. Okay? We're gonna do it through the center of gravity. All right, let's go. Now, as it relates to clockwise moments is the force that will cause the rod to rotate in the direction of the clock hand around the pivot. And the anti-clockwise moments are those that will cause it to rotate otherwise. So this force here, T2, will cause the thing to rotate that way. And this force here, 10 newtons, will cause it to rotate that way. However, this force here will cause it to rotate this way. So these two here are the anti-clockwise. That is speaking of. This one is anti-clockwise. And this one is anti-clockwise. But this one is clockwise. All right, so we said the sum of the anti-clockwise moment must be equal to the sum of the clockwise moment. All right, so let's take a look at that idea. So you know this force of the 40 Newton will be, because that's where we're acting as the pivot, a force has no turning effect through the pivot. All right, so that force, even though it is effective, is basically not affecting the rotation of the thing around that particular point. So here we go. Clockwise moments clockwise moments. So the clockwise moments is going to be equal from the center here to the force, the distance from the pivot to the force, and that's going to be 3 centimeters times T1. All right, and that's the clockwise moment, and that must be equal to the anti-clockwise moment. So let's find the anti-clockwise moment, those that will cause the thing to rotate in a clockwise direction. And first one we have is from here to T2. So that's going to be 3 centimeters times T2 plus this 10 Newton times the 1 centimeter. So 1 centimeter times 10 Newton. Now, obviously, notice that over on this side, T1 just needs 3 centimeters to multiply to make up all the clockwise by itself. But the T2 here needs another additional force, which that means, therefore, that T2 is smaller than T1, because T2 needs help to balance T1. You see that? So T2 is smaller than T1. Where do we see that? Here we find it right here, D. T2 is smaller than T1 as a result, because T2 needs an additional moment to equalize on the anti-clockwise side to what is going on with T1 on the clockwise side. All right, that's just the simplest way to just get straight to the answer. Just calculation could be done to find answers, but that's not what we were asked. All right, that being said, number 9, it says, which of the following is used to calculate the efficiency of a machine? So which of the following is used to calculate the efficiency of a machine? So what normally happens when you're talking about the efficiency of a machine, you look at the amount of power you put in. So the amount of power in, right? And the amount of useful power you are able to use. Some of it is going to go out to wastage, and that you cannot do anything about. So the power out over the power in, and since it's percentage, then it's times 100, right? Times 100. Now then, so the power in would be likened to the effort. Sorry, what am I writing? That's the effort that you put in, right? Times the distance that you're able to apply that effort, compared to the load that you're able to move with that effort, times the distance that load is able to go. All right, so if we consider this are different These can be different. All right, so which one takes on this? So we say load times distance moved by the effort, load times distance moved by the load, times 100. That's C. Load times distance moved by the load, effort times distance moved by the effort. And that's the one I have here, right? So that's B as in ball joint. Or, you know, for those who are driving and you really wanted to know that you're really jointing. Anyway, continue. All right, so this item here, item 10 to 11 refer to the following: velocity time graph. And I stress velocity there, which means that it's not speed, it's velocity. It's not distance, it's velocity. All right, so the thing is already moving and you're tracking that constant motion in, and remember that velocity is a vector type quantity, which means it's tied to a direction, as opposed as in comparison to speed, which don't care about the direction, just care how fast something is going. All right, or the distance covered, the average distance covered in average amount of time. All right, let's take our total amount of time. So let's go again. So refer to the following velocity time graph, which shows a ball being thrown vertically upwards from the ground. Downward motion is assumed to be positive. So that means whenever the ball is going down, we say it's positive, all right? Whenever you see negative, we say that it's going up, all right? According to the graph. Downward motion is assumed to be positive. The point X on the graph shows when the ball is. So notice this is at the point when the ball is at 0. Wow. 0 velocity. What does that mean? Well, I don't know if you guys ever noticed this. You probably threw up a ball before, or a stone, a stick, a shoe, a toy. And you know, old people say, whatsoever goes up must comes down, right? So when you throw up that ball, shoe, or whatever you throw up, it goes up, and as it goes up, gravity pulls against it, which is why they give it negative for going up, because gravity acts negatively against it, causing it to slow down. But if it's slowing down, and it's going to turn around, it must first come to a stop. So at some point into the year, in some moment of time, it stops before and then turns around and starts speeds back to the ground, because gravity is still acting on it and causing it to accelerate and moving fastly, shooting come at you. That point X on the graph tells where it goes to. Notice that the velocity is 0, and that's when it's reached its highest point. Because remember, it's going to turn around now, so it's not going to go any higher. So at the highest point above the ground is when the velocity is 0, and that's when it will turn around as well. And gravity will now start works to pull the thing down and cause it to speed up. And that's why they're saying they're going to give it the positive numbers from that. It says the gradient of the line PQ represents the. All right, so if you notice, the gradient is on the y-axis. So I would have V2 minus V1, which is a change in velocity. And I'll have it over time. What is change in velocity over time? Change in velocity over time is A, acceleration. Acceleration is the rate of change of velocity. So if you were to find the gradient, remember, to find gradient, you do what? Gradient M is equal to rise over run. Now you will remember that if you are rising up out of your chair, you go up. Or if you say negative rise, you sit down, right? So rise is the up and down motion that's along the y-axis here. And run, you run across the ground, right? So across the ground is along the x-axis like that. All right? So if I follow rise over run, rise is the difference in the two y values. So the final y value, y2 minus y1, the difference in the two y values, the change in the two y values will give you the rise. And the change in the two x values, x2 minus x1, will give you the run. Now, if you notice, time is measured on the run axis. So the change in time, so that's why we put time down here, right there in seconds. And the change in velocity, which is measured here on the y-axis, is measured here, and the change in velocity over the change in time is equal to acceleration, the rate of change of velocity. Yes, I know. It sounds beautiful, don't it? I love it too. All right, so no, this weird thing has the things all over this. All right, so let's go again. We're at question number 12. Refers to the following item. All right. And even before reading this question, it appears to me very obvious that these are some things like marbles, and this has to do with collision. Now, collisions are of two types. There is what we call the elastic collision, and there's the inelastic. All right. You want me to write that down? You want me to write that down? You don't want to spend elastic for yourself. All right. Let me write it. Elastic and inelastic. All right. So you may be saying, all right. So you say, sir, what's the difference? All right. Since you asked me, I'll tell you. No, elastic. Well, if you have an elastic band or something that is elastic, it can stretch apart, right? It can stretch apart and come back together. So what happened in the elastic collision is that the two things collide, but after they collide, they go apart. So one goes that way, and and the other one goes that way, like they are stretching apart. The distance between them is stretching like an elastic band. Elastic collision. Inelastic collision means it's not elastic. So if it's elastic is when they're going apart, so they must not be going apart then, which means that what happened is that this case, they come in, as before, but after this now, they stick together and they move together. Whether they move together this way or they move together that way, they are stuck together and they move together as a unit. Inelastic, not stretched apart, no space in between them. They're moving together. That's inelastic. So elastic, they're going apart. Inelastic, they are staying together. Now, whether it is elastic or inelastic, you must know this, that the sum of the momentum before the collision is equal to the sum of the momentum after the collision. This comes from the law of the conservation of momentum, which comes from the law of the conservation of energy. Yeah, you're saying, sir, where's the energy in this? You don't know about kinetic energy, the energy that things possesses while they're moving? Oh, come on now, like, duh. Please. Anyway, that being said, momentum, how do we, momentum, this is the symbol they use. I'm going to give you a different color. Let me give you a little red. All right, so they give this little slanted P for use of momentum. They also use the same symbol. It's called rho, R-H-O, a Greek letter. And they use it for pressure as well. So, based on what you see on the other side, you must know what it is. For pressure, it would be mass times height times, acceleration due to gravity, or, weight times height. But here we're taking a look at did I say pressure? No, I meant to say density. Anyway, let me go back to this. So momentum is mass times velocity. That's it. Mass times velocity. So you can have a M1, V1 at the beginning must be equal. So the sum of the velocity, the momentum at the beginning must be equal to the sum of the momentum at the end. And please know that momentum having velocity in it, and velocity is a vector quantity. So the direction, the direction does affect the sign, whether it is negative or positive, and affect how the sum turn out. All right. All right. Now that you have gotten that little bit of introspective, let me know. No, let him try. So let's go to the question. X, Y, and Z. Now notice that X is coming in at 20 meters per second. All right. X, Y, and Z are 3
To try, but it's not. Try.
X, Y, and Z are 3 billiard balls. And if you know billiard, it's something like pool, where they have the little table with the holes that you knock the things in. All right? 3 billiard balls of equal mass whose centers lie in a straight line. They're just simply saying they're the same size, same mass, so all of their center of gravities are alike. So basically, they tend to have linear momentum, meaning that when they hit each other, they're going to go in straight lines instead of, turning and curving. Continuing, so yeah. And so Y and Z are touching each other, as you can clearly see right here. You can clearly see that those are touching each other. And they're making sure to tell you that because they're being together. And they are stationary, which means they're not moving. So if they are stationary, their mass times their velocity is whatever their mass is times 0, and 0 times any number is 0. So their momentum is 0. So if you're not moving, your momentum is 0. Hello? Okay? And yes. And X traveling at a velocity 20 meters per second. 20 meters per second impinges on Y. Assuming that the spheres are perfectly elastic, the resultant motion after impact is? So let's see now. X, Y, and Z are all moved together, each with a velocity of 10 meters per second. Well, they can't move together. And the reason why they can't move together is because it says that the answer is that they should be elastic. Remember I said elastic? They stretch apart. Right? They move apart. X and Y remains stationary while Z moves on with a velocity of 20 meters per second. That can be considered elastic. These two, so what they're essentially saying is that these two instead get stuck together, and then that one moves. That is elastic because there's some going apart. X, Y, and Z remain stationary. If X, Y, and Z remain stationary, that means the entire momentum would be 0. What happened to the momentum that came in? Where did it go? All right, so that would be a problematic. X remains stationary while Y and Z move on together with each other of a velocity of 10 meters per second. All right, so now this is a very real possibility as well. So this is a very real possibility where the momentum could be shared in terms of the velocity between the two, right? And they move with a velocity of 10 meters per second together. But the issue with that is because there are 3 of them that is least likely to happen. Because what will happen is that the collision into Y will cause transfer momentum to Y that transfers momentum to Z. And so you're more likely to have B happening than D because there are 3 of them. If it was 2 of them, Z would be a great possibility. All right, so here we go again. If we take a look right down here, item 13, it refers to the following diagram showing a positively charged sphere, A and B suspended by an insulated thread. Now, the fact that they mentioned that the thread is insulated, you should know that insulators do not conduct electricity or heat. Well, no, the fact that they said sphere charge, mean they're talking about electrically insulated. So they are electrical insulators. That means they don't allow charges to flow. Once a charge come on it, it is stop where it is at and it don't move, does not conduct electricity. Well, all right, that being said, it says A and B, 2 positively charged insulated and it's an insulating thread. So what does that mean? Well, what that means is that if A and B are positively charged, you should know that unlike charges attract, but like charges repel. Positive is like and like charge. So they're going to repel each other. All right, so A and B are going to repel each other. Now, if the spheres come to rest, as shown in the diagram, the force keeping them apart is the, all right, it could not be the gravitational force. The gravitational force would pull down on them and kind of cause them to want to come back towards each other. It is electrostatic force. Let me just say that. So it is the forces that occur between charged particles because they are charged. It says that these spheres are charged. They are positively charged, and that forces them to repel each other. All right, and that's why you see this distance between them. If the thread was not insulating, the charge would run up the thread and go away and cause them to the repulsion to be less and cause them to come nearer to each other. All right. That being said, here we go. Question number 14. Which of the following tools are designed to take advantage of a large moment Which of the following tools are designed to take advantage of a large moment provided by a relatively small force? So you put a large moment provided by a relatively small force. And as you can clearly see here, there are some instruments. You have the claw hammer, the crowbar, pair of tweezers, pair of wire cutters. All right, so let's talk about the claw hammer now. So the claw hammer would be something like this. And then you have the claw at the end here. Then you will have the handle like this. You put in a little force here, and then it rotates about the pivot here and causes the nails to be pulled up right here. All right, so you put in a little force to get out a great effort. So the claw hammer does do that. Take advantage of a little force. The crowbar. So the crowbar works similar to the claw hammer, but is shaped long like that. You put in the nail or whatever here, apply a little force there, and it will pull out the nail. So the crowbar also does that using moments. A pair of wire cutter now is the same thing like scissors, right? All right, so the wire cutter is something like this. Is basically a scissors. You apply a little force in this direction, and then that applies some force right there, causing the thing to be easier to cut. So using the principle of momentum, but tweezers now. The tweezers, and you guys know tweezers, especially the ladies, you know, always tweezing stuff. Tweezing bumps, hair roots, and so on. You apply your forces here and here, and the forces that you apply, you have to resist the elasticity of the metal and then grip the thing. So it's just the force that you apply that produces the effort inside right there. So the tweezer don't make use of any movement. All right. So if I should, you know, just clear these things. So which of the following tools take advantage? So it's this one, that one, that one. 1, 2, and 4. And that's D as in dog. All right. Which of the following is a unit? Which of the following is a unit of work? All right. Now, work is energy, right? And it is the force applied to an object, moving the object in the same direction as the force, and it moves it for a distance. So this says W, which means work done. Work done is energy, so it's a measurement of energy. Of course, you see this is, and it can be measured in joule, but this has Newton meter. It's something that it can be. So do we see Newton meter here? All right, so this, it can be Newton meter, but Newton meter is usually reserved for moment of a force. So let's go again. Can it be Newton per meter squared? It cannot be that, because as you see, this is meter, not per meter squared. Can it be kilogram per kilogram meter per second squared? That's mass times acceleration, that's force. But can it be joules per second? Okay. Let's think about all of that. So if we look at force, Newton, as being mass times acceleration, it's going to be kilogram meter per second squared times meter. So this is what force is, mass times acceleration times meter. We would get kilogram meter squared per second squared. And so this idea with the joule per second, could it be that? No, not going to be that. So we're going to have to go with Newton meter. All right. And here we go again. When a car is moving at a constant speed, the energy changes occurring are. So when a car is moving at constant speed, which means that the amount of distance it's covering per unit time is not changing. It's the same all the time, right? The energy changes occurring are, it says chemical energy to kinetic. Is that so? All right. Chemical energy to potential. Potential means it's storing up the energy, but the chemical energy is already the stored energy. It is called chemical potential energy. So you see, it can't be that. Kinetic energy to potential energy. So is it taking the energy as in motion and storing it up? No. Chemical energy to nuclear? No. So it's the first one. It takes the chemical energy from the fuel, and as it burns, it causes the gas particles in the engine to expand and move, transferring that motion to the pistons, which transfer that motion to the crankshaft, which transfer that moment to the transmission, which transfer that moment to the driving shaft, which transfer that moment to the wheels. So it's just chemical energy to kinetic energy, which is the energy you possess during motion. All right. And here we go down here. Item 17 refers to the following diagram, which shows a dam. Here's the dam, water. Okay, so dam is basically infrastructure that is built up to store water or to back up water and then control the flow of that water. Now, the reason for creating a dam, instead of just letting the water flow normally, is that as the water is backed up by the dam, the water level rises to get over the dam. And as the water level rises, they'll have a higher water level and they can do whatsoever they want with it. Let's say they want depth, like a swimming pool. I know people that goes to dams and swim, very dangerous. I don't advise anybody to do that. Right? So the pressure on the dam at the bottom of the reservoir depends on. So they're saying if we go to the dam right here, right, well, let me first clear all this. What is the pressure of the water going to be at the dam at the bottom there? So the pressure of the dam at the bottom, see there it says bottom of the dam, reservoir depends on, and what is going to depend on is the depth of water. Right, the depth of water. How high the water is. The higher the water is, the more column of water, the more mass pressing on mass that will cause the weight of that water to pressurize anything below it. All right? And as a result, it's just going to be based on the depth of the water. All right, that being said, let's scroll.
But after a while, Lance notices that Ash is gone. It's zoned out like a dull pen. But here's the article yelling that for the story.
All right, so here we go now. A piece of string is tied onto a small stone and the stone is then suspended. So, piece of string tied to a small stone and then the stone is then suspended. Totally immersed in water. The tension on the string will be, all right, so let me give a little diagram of what they're saying. So here's the stone on the string and the string boom. Then they put the stone in water. Now, please note, the weight of the rock is going to act down. But then the water is going to push on the rock. And that is called the upthrust U. Right? The upthrust caused by the water going in the opposite direction to the weight is going to cause the effect of the weight to be lessened. All right? So let's see, so it says the tension on the string. So the tension is going to be this force on that string right there. So the tension on the string. Now, before the rock went into the water, the tension on the string was equal to the weight of the rock. So the string had to bear all the force to hold up the rock so it don't get continually pulled down by gravity. But now that it went in the water and the upthrust is assisting the string don't have to bear all of that load anymore. So the amount of force that the string will have to bear is now lessened because of the upthrust acting on the rock. And so the tension on the string will be 0, no. Equal to the weight of the stone, no. That was before it went in the water. Less than the weight of the stone, yes. Before it was equal to the weight of the stone. Now it is less because it has additional force assisting it. So it don't need that. The tension don't need to kill out itself to hold up the rock anymore. All right, that is what happens there. Let me clear this. Let's go to question number 19. A solid object, when placed in a beaker of water, just sinks to the bottom. Which of the following should be done to make the object float? So an object, when placed in a beaker of water, sinks to the bottom. Which of the following should be done to make the object float? All right. Cutting off part of the object. Will that make it float? No. Because the reason why it's sinking is because the density of the object compared to the water is greater. So the amount of liquid that object can displace, or the amount of water it can displace, the weight of that water is going to still be less than the force that object is creating on the water. Dissolving a lot of the water, dissolving a lot of salt in the water. Yes, if you dissolve a lot of salt in the water, then the water itself will get heavier and cause the comparing density of the two objects to the gap to be closing, right? The relative density to become less. Carrying the beaker up to the top of a high mountain, that does not do anything in this case. as it has to do with a play with densities. So here's what we're gonna say now, and the answer is just 2 only, which is B. So you change the density of the water, and that will give an effect. Number 20, all right, so here we see a syringe, and here's the piston of the syringe right there. And it is gonna affect the volume of whatever is inside the syringe in this part here. Okay? It says 24 cm cube of air at pressure P millimeter mercury are trapped in the syringe, which is blocked at X. So they're telling that right X here, so it's blocked. It's blocked at X. If it's blocked, it can't go through. The piston is forced to the 8 millimeter mark. All right. So the piston is forced to 8 centimeter cube mark. The new pressure in terms of P is, okay, assume constant temperature. All right, so we're looking at this law now that says pressure is inversely proportional to volume. So if you increase the volume, that will decrease the pressure. If you decrease the pressure, that will increase the volume. And so if you were to multiply P1 by V1, you're going to get a constant. And then if you shift it to P2, then P2, V2 is going to give you. So you're going to get a constant by multiplying P1 by V1, which on the next side, even though the dimensions may be different, the product of the two of them will come out to be the same thing as well. So let's take a look at that. So originally, the pressure was P. It's called, yeah, P. And it was timed by 24. 24. I'm just gonna write 24, right? And that is gonna be equal to P2 and V2, which is gonna be 8. So they're asking the new pressure of P. So to find the new pressure of P, which is P2, I just carry this across over here. And if we're gonna get 24 divided by 8, which is 3 times the original amount of P. So that's 3P. That's 8 into 24 goes 3 times. So the pressure is going to be 3 times as large in order to get the volume 3 times as small. All right, or basically to get the volume to 1/3 of its original thing. All right, let's clear. Let's go to 21. In the pressure law, which of the following would be true? So in the pressure law, which of the following will be true? The ratio of pressure to Kelvin temperature is constant. Volume is constant. Pressure is constant. All right, so in the pressure law, what we're doing is that we're saying the pressure is directly proportional to the Kelvin temperature. Right? And if you were to carry this across, you'll get a division. So it would be P1 over T1. That is going to be the constant, actually. But anyway, so that means the ratio of pressure to Kelvin temperature is constant. Yes, that is true. Because once they're directly proportional, it means that their ratio is constant. The volume is constant. Well, as you can clearly see, the V is not in it. So this is constant, this is constant. The pressure is constant. No, the pressure changes with temperature and the temperature changes with pressure. All right, so it's just 1 and 2. And that is C right here. All right, so here we go again. Which of the following are characteristic features of a clinical thermometer? Clinical, I want to like circle that word clinical.
Oh.
Clinical meaning from clinic, which have to do with medicine, the body, health. So the thing about a clinical thermometer now, it has a narrow constriction in the tube just above the bulb. That is true. Why does it have to have a narrow constriction? So that the effects of the temperature on it will give a bigger rise so that you can see it more vividly. Because you want a more accurate reading of the body temperature. You know, so you want it to operate in a more narrow margin. All right, next again, limited range of temperatures. Of course, it's limited range of temperature. If your body temperature passes 42, 43, you're in critical fever thing and you're going to more than likely pass out, go in a coma and stuff like that. So your body temperature is not going to go higher than, say, 43. And as it relates to going lower than, say, 36 or 35, going less than 35, you're going into hypothermia and your body begins to shiver and so on, and your body may even lock down. So it has a limited range in which it operates of somewhere between 43 degrees Celsius to 34 degrees Celsius, somewhere in there, because your body temperature by normality must be somewhere in there. So, all right, so it has limited range of temperature. Large bore to make a mercury more visible. Large bore. What are they calling the large bore? If they're calling the reservoir, right here, so no, the reservoir will be large, but the bore has to do with when it comes out through here. So the bore cannot be large, because if the bore is large, what about the narrow constructed bulb? So it's gonna be 1 and 2 only, which is B. You can have constricted tube and having large bore. Like those two don't work together. All right. Now let's go again. Which of the following are reasons why a hot liquid placed in a double wall vacuum flask retains its heat for a long time? Right. You asked for a double wall vacuum flask. What is that? Basically, they're saying a thermos. So the first thing is that the thermos all right, so that is the first part. Then it has air. So air or vacuum inside here. So this is a mirror. This part is a mirror. It is silver coated. And this part is silver coated. And I'm going to tell you the reason why. And usually the silver part is made of glass or something, glass or some are metal. And then they have plastic outside of it here. And styrofoam to hold it in place like that. And of course, they have a cap. So what is it about this that keeps the heat in there for so long? So which of the following reasons why they hot liquid in the double wall? So double wall, so here's one wall inside here, and then here's the other wall here. Vacuum flask retains its heat for so long. Evacuated space between the double wall reduces the loss of heat by conduction. That is true. You can't conduct heat across a vacuum or across air. So that's inside it. So I'm gonna put this in red to show you what they're talking about. They're talking about the space in here being a vacuum stops conduction of the heat, and that is true. All right. Silver inner walls reduce the loss of heat by radiation. So what happens is that when the heat rays come on the wall, it bounces back because of the reflective surface. When it comes in here, it bounces back. And so it's trapped in there because it keeps bouncing back. The silvered outer wall helps to absorb heat from the surroundings. Well, that's not what it does. So it's just the two that I mentioned. All right, so these two. The silver wall here is to also further reflect any heat that passes through that wall, it reflects it back into the flask like that. All right. All right, so we're gonna go to 24 now. So here we go. Which of the following is longitudinal in nature? All right, so there are two types of waves. So what a wave is a disturbance, right? So you create a disturbance, and as that disturbance tries to propagate itself or travel or move from where it is, that's when you create a wave. So if the particles go up and down and up and down and up and down and up and down and up and down for the wave to travel that way, we notice that the particles go up and down like this, but the wave travel across like the arrow. So they create a T pattern, that's a transverse wave. But sometimes the particles may go back and forth like this, back and forth like this, back and forth, back and forth, back and forth, and the wave travel like that. So what you find is that you find sometimes the particles, they go in together, and then sometimes they stretch out far apart. So you call them compressions and refraction, and the wave travel in that direction. So notice that the back and forth movement of the particles is in a parallel line to the same line as the wave. So it is along the wave, along the direction the wave is traveling, or the wave travels along the direction of vibration. So that's longitudinal. Get it? Along. Okay. Take you some time, but you'll catch up. All right. So that's the point. So let's take a look at the waves that will obey this kind of pattern. And infrared comes from the electromagnetic spectrum family. So this is transverse. So that's T. Light rays come from the electromagnetic. All the electromagnetic spectrum family are transverse waves. They're all similar. So light waves is from the same family. Water waves can be both. But when you're talking about water waves here, you're talking about when you look out on the water and you see the waves going rippling up and down. So if the particles are going up and down, but the wave is traveling outward, that is of course transverse. But if you have sound wave traveling in water, then that sound wave in the water is longitudinal. Sound wave is the actual thing. Sound wave travel like this. As a matter of fact, it is the most common wave to travel like this. All right? All the others usually are transverse. Which of the following graphs illustrates the variation of pressure with volume for gases obeying Boyle's law? All right. So gases and so the variation of pressure for gases obeying Boyle's law. So which of the following? So they have the pressure volume thing going, right? So notice remember I said earlier that the pressure is inversely proportional to the volume. So as the pressure increases, the volume must decrease. But notice this 1 over V, so it don't decrease in a straight line, so it decreases in a curve like this. So this is the one right here, so that we're looking for, D. So notice that the volume is going, the pressure is going down as the volume is going up, but it's going along a curve to represent this 1 over V idea here.
Finished bathing screen pumps, but she screamed that she needed her pump free. He tried telling her that his green.
All right, 26. A gas is much easier to compress than a solid or liquid because the gas molecules, all right, so these are very numerous. No, it's not. Are moving very rapidly, have no forces between them, are arranged randomly. And the whole idea with gases is that the particles are so spaced apart that you have room to put them together, to compress them. The solids are already tightly packed, so there's no more room to bring them any closer. And the liquids are also tightly packed, but they're able to move around, they're able to slide past each other. So they have a very little room for compression, but hardly any. And so it's just because of the arrangement of the particles. The particles in this are arranged widely apart. They put randomly, but it really should be spaciously or widely apart. All right. Let's go again. A fixed mass of gas at constant temperature is compressed. Compression, constant temperature. The molecules of the gas will. So let me try and, give you a visual of what is going on here. So, all right, so this is the piston, and I'm going to put 2, 3, 4. So I put 5 particles in there. Then and if you push this down, you still have to have the same 5 particles. And they're in a smaller space, as you can clearly see. Okay, this one fix it. All right. So let's go back to the question now. It says a gas is much easier to come. Okay, we did that already. A fixed mass of gas at constant temperature. So the temperature is going to remain the same. It's compressed. The molecules of the gas will hit the sides of the container more often. And that is the answer. Here's the reason why. If you lessen the distance between the walls, then it's a shorter distance for it to knock one wall and then go back to the other. If it's traveling at the same, with the same amount of energy as before, similar amount of energy before. And of course, the space being smaller, the particles will collide with each other more often. And that increase in the hitting the sides of the container will also is why the pressure also increases. Because it hits the container more, creating more pressure on the walls of the container. If their temperature remains constant, you can't say that they have more kinetic energy. All right? And you can't say that they have less because it's whatever. So it's just that it's going to hit the walls of the container more because it's going to take less time to cover the space. Finish now. All right. Which of the following waves has the greatest amplitude? Now, amplitude of a wave is how far from the equilibrium line, the particle oscillates up or downward to carry on the disturbance. And if you can realize, this one, the highest particle is higher from the equilibrium line than this one. And it's higher than this one. And it's higher than this one. It's directly between everyone. So this one has a greater distance from the equilibrium line, which is this dotted line going across. Excuse me, Mr. All right, so let's find 28 to 30, no? Okay, I'm not finding 28 to 30 right now, so okay, what we'll do, I'll just pick a few more questions from somewhere. And all right, so here we go. Let's just take a few questions from here, the 41 to 44, and then we're going to take a look at what happens on the paper 2 type questions. All right, so here we go now. Which of the following relationships between the electrical quantities is correct? So which of the following relationship between the electrical quantities is correct? So let's take a look at all the electrical formulas that we may be familiar with. All right, so we know that I is equal to V, sorry, I should write as V over R. All right, and if we do the magic triangle, all right, regardless. So this formula here, where it says R is equal to VI, R cannot be equal to VI. R must be equal to V over I, as we worked out earlier. All right, so this one is out. Now, they say power, electrical power is equal to IV, the current times the potential or the force pushing that current, IV. And so if we were to find V from this, V would be equal to P over I. All right, and not this, so this is out. Then we have two more, and that's E is equal to VT. All right, so here we have a formula here that says Q is equal to the current times the amount of time it takes for that current to flow. And that the energy by a charge is equal to the charge and the voltage, QV. So if you notice, if I move this over here, I will get Q. So this is the correct answer right there. All right. Here we go again. The speed of light is highest when it passes through a vacuum. The reason being is that in a vacuum, there's no particles to interact with it to slow it down. Nothing is in your way. What's to stop you from going as fast as you can? Nothing. So in a vacuum where there's nothing to slow it down. So it is fastest in a vacuum. Then it's just about as fast in air as in a vacuum because the air offers a lot of spacing. Then it is next fast. It slows down a bit more in water and it slows down the most in glass of these four things that are placed here. All right. So glass out of the four things is said to be more optically dense. 43. The total internal reflection in a medium occurs only when the angle of incidence is greater than the critical angle, and that is correct. You're saying, what is this critical angle? Well, if you think about a block, and I'm going to consider inside this block to be glass. I'm going to put glass here. And out here, so to be air. So let's say some light beam came into the glass and it is going to hit the surface of the glass like that. We put a normal, which is an imaginary line perpendicular to the surface or the boundaries. If this angle here, theta, is greater than the critical angle between the two things, then what will happen is that this will bounce off the surface there, the boundary, and stay inside the material. If it is less than the critical angle, it's going to go back out on the other side of the boundary. So this angle here is all angles are measured away from the normal, right? So if the angle of incidence is greater than the critical angle, hey, you know what happened? You got to stay bouncing around, baby. All right. The refractive index of a transparent medium with a critical angle of angle C, for a light traveling from the medium to air is, all right, so how do we find this critical angle is the question. Now, usually for, let me use a different color. For light going in, right? We call this angle I, and we call the refracted angle, the bended angle inside, R. So that sine I over sine R is equal to N, which is the refractive index. Right? Now, if sine I reaches the place where I is 90, sine of 90 is 1, then what you'll have is 1 over sine R is going to be equal to N, but guess what? N right here is going to reach C here, so it's going, so 1 over the sine of the critical angle is going to be equal to the refractive index, because at this point the angle of incidence would be at 90 degrees, making sine I 1, right? And if that is the case, the refractive index of a transparent medium with a critical angle C for a light traveling from the medium to air is, okay, all right, so yeah. So it is this formula that I have here, 1 over sine C is equal to N. All right. Or you can switch them and say 1 over N is equal to sine C. Let's look at where we find that. Here it is. Notice, I said sine of 90 is 1, right? So if sine of 90 is equal to the 1 right there, and sine C is equal to that right there. So that's it. All right, so this is the answer. That's what I'm saying. All right, so what we want to do now is to take a look at a few longer questions.
But as he approaches the boundary, the super bubbles and the bear comes to the ground. This they know that he has untied the bear's which is something else.
All right, so we're gonna go with June of 2019 and see like how many of these questions we can take a look at. All right, so here we go now. Figure 1 is a diagram of a transformer. Name the parts labeled X, Y, and Z. So many of you may not know about transformer. It's a electromagnetic device that transfers power by electromagnetic induction and is able to change the voltage and current by virtue of the amount of windings and compared from the primary to the secondary. The primary coil or windings is where you input the original power from the source, and the secondary winding is where you induce that power to be transferred into another coil that is not touching, that has no direct connection to the primary coil. That other coil is called a secondary coil. And based on the number of turns in the secondary coil as compared to the number of turns in the primary, you can either increase the voltage or decrease the voltage, increase the current or decrease the current. All right? In such a way that the V times I, which is the power in, must be equal to the power out in ideal conditions. That means assume that there's no energy loss. Of course, there's no ideal transformer, so you have efficiency, but that has not come up in the question as yet. So we'll save that for a later time. Figure 1 is a diagram of a transformer. Name the parts labeled X, Y, and Z. All right, so they already said that X is primary. All right, so here we go now. X is the source power. All right, so X is the source power. What is Y? Y is the secondary coil or winding. What is Z? Z is usually an iron or slash, sorry, a electromagnetic core. Let me not use the word electromagnetic. It's an iron core or it's a iron core. Usually it's an iron core. So it's usually a core that allows the formation of magnetic field lines to be built up and collapse inside of it. All right, so iron core, and it's usually laminated. It's usually a laminated iron core. And if you're wondering what laminated means, it means it has layers. So instead of us having, let me show you, you could have a piece of iron that is like that, right? And I'm going to draw the same piece of iron again. But you can have it laminated like this. You have it in layers. And then what you do now is you put some kind of separation between each layer.
Excuse me twice. Thank you, Mr.
So this blue here is some insulated separation, usually some kind of glue that holds them together, but separates them at the same time. So if the yellow part is the iron, instead of having one big solid block of iron, they have different layers of iron to carry this. Now, the reason for that is it reduces the amount of heat that builds up in the core and waste and lessens the amount of energy that is waste, making the transformer more efficient. All right.
Basically realized that they had fallen for a plan. And it seemed the architect that built for something recalls what happened there. He states that he had noticed.
Okay, so here we go again. Now the transformer shown in figure 1 is tested and the values of the primary voltage VP and the secondary voltage VS were obtained. The data is shown in the table 1 below. So here they are. So when the primary voltage is at 1.5 volt, the secondary voltage is at 14. Primary voltage is doubled to 3. The secondary voltage is a little bit less than double to 26. So there's a little bit of voltage drop, or loss of voltage. When it goes to 5, which is more than 3 times 1.5, then this is, which is, goes to 6 is 53 and so on and so forth. Using the grid on the graph 7, plot the graph of VS against VP. All right, so let's do that. So VS against, now the fact that they put VS first means that VS must go on the y-axis and VP on the x, all right? So the y, so when they state in the name, it's like that. All right, so here we go now. I'm gonna draw. All right, so VS will be along this axis in terms of voltage, and VP will be along this axis. All right. Now, all right, so VP goes up to 8, VS goes up to 72. All right, so let me see, hold on. So let me see now. So if I should make this go up to 72, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 into 72. What's the answer we get? So 72 divided by 21, I'll get 3.4. So we're just going to make each of these boxes be like 4. Okay? So here says 0, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60, 64, 68. 72, 76. All right, so you see we make it. And then on this side now it goes up to 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. And if you think about 16 divided by 8,
Thank you, my friend.
you get 2. So for every 2 of these boxes, we're going to make it 1, 2, sorry, 3, 4, 5, 6, 7, 8. All right, so there we go now. Now, they say when it was 1.5, it was 14. So 1.5 is half of 2 is half of 4 is 2. Half of 2 is 1. So it's somewhere here. Sorry. What am I doing? Yeah, 1.5, which is this. Goes up, goes up, goes up, goes up to 14. Which is halfway between 12 and 16, right? Then when you went up to 3, remember that the answer was the 26. And then when it went up to 5, oh my, sorry. Something, this is 3 right here. So it must be here. Then it went up to 5. And it went up to $45. So 14, 26, 45, 53. So at 5, it should be at 45. So this is 44. This $42, $44, $48, $46, $45, somewhere here. Then at 6, we remember it was at 53. So this is 56. 54, 53. And then we had 7.5. So 7.5 to 67 and 8 to 72. So 7.5 to 63, 60, 64, 63, no, 62, 63. 8. Is it 63 or is it 67? It was 67. My bad. 67. So this is 68. This is 64. This is 66, 67 is somewhere here. And then at 8, it is 72, which is here. All right. Now, by the looks of this, this thing looked like it wanted to be a straight line. But all right, now you have to use the graph of best fit. So notice that this graph I'm drawing now as is, 2 of the points are on the line, 2 are above and 2 are below. So we'll work with this, okay? As a graph of best fit. What do I mean by that? So notice we have these two. We have these two above the line and we have this one and this one below the line. So you have to try and make it evenly distributed about the line, all right? Now, this is our graph of best fit drawn from this. The question that they asked next was, using the grid on 7, plot a graph of the, all right, so we get 8 marks for that plot. Determine the gradient S of the graph. So we're going to come to determine the gradient now. All right, so this is our graph. The title of the graph is VS against VP. So you write that at the top. You label this side over here VS as I did, and VP over here. You put on your scale, and you put the units in which they are measured in, which if I should. So this is VS. This is VP measured in volts, measured in volts. All right. All right, so we have that. Now the question asks us to find, well, and right up here would write VS against VP. Anyway, let's go to the gradient now. So to find the gradient, we need to make a gradient triangle. Or some place where we see like this thing look like it exactly hits some of these points. I don't know. I am tempted to use this one. All right, let me use a different color. So notice making a broken line triangle. And I'm going from the 0, 0 point. And of course, I'm going to be using rise over run, like you saw me explained earlier in the multiple choice. So this is the rise. This side of the triangle. And this side is the run across. Now notice that the run goes from 0 to 5.5. All right? So the gradient S is equal to, and we can put rise over run, which is equal to 5.5. And then now, what's the run now, the rise now? This rise is go to here, that point there. This is 48, halfway between 48 and 42 is 50. All right, so 50. All right, so if we divide 50 divided by 5.5, and we get 9.01. 9.0, sorry, 0.09. All right, that's the gradient. And if it is voltage divided by voltage, the answer don't have any units. All right, so the gradient work out to be 9.09, or rounds off to 9 to the nearest whole number. Now we soon see why the nearest whole number thing is important. So remember this triangle that we make, and you try to make the triangle using points that you can clearly identify the values for, all right? So that is the reason why I had chosen this point. And I had chosen the 0, 0 point. There's no missing the 0, 0 point. So I could make out that this was halfway between 2 points, and this was on a direct line that was halfway. I could make out the values for that. So that's why I chose those. So I could get this nice little rise and this nice little run. All right, that being said, so we have answered this question about determining the gradient S of the graph. So we found S, and S is 9. Use the gradient S to calculate the number of turns in the secondary coil, NS, given that the number of turns in the primary coil is NP is 85. All right, so now I'm going to clear out this. Now this value S, the gradient, has to do with the ratio of one to the other. So I'm going to round it off to 9, because it's usually a whole number. So it's just for the loss in voltage that you may have this decimal being there. So run off to the nearest whole number. And I'm going to clear this. And we have S to be 9 already. So we have S is equal to 9. All right, so the number of turns in the secondary coil, S, given that the number of turns in the primary coil. So here's the thing now. Are you ready? If VS, right, over VP, what am I doing? Over VP is equal to 9, guess what? So is NS over NP is also equal to 9. So then all I need to just write is that the 9 ratio is equal to NS, which we don't know the value for, over NP, which is 85, And then to get NS by itself, we carry this up and multiply over there. So NS is going to be equal to 9 times 95. 85, sorry. So, and NS is equal to 765 turns. All right? So 765 turns for NS. All right, and that's how we work that out. Now, the next part of the question says the current in the secondary coil, IS, if the current in the primary coil is 1.8 ampere. All right, so watch this though. So the thing about it is that because the current decreases when the voltage goes up, it's going to be the reverse as it relates to the current. What do I mean now? So I'm going to write. So NS over NP, which is equal to 9, is going to equal to the current in P over the current in in S. See? So notice that these two are inverted. Instead of having them match up as IS, NS, you invert them. So now I'm going to write again 9 is equal to IP over IS. They tell us that the current in IP is 1.8. So I know that this is going to go up here. And so I'm going to end up with IS is equal to IP divided by 9. But IP is 1.8 ampere divided by 9. And that's going to be equal to 0.05. Zero 0.2. 0.2 ampere. And please note you had gotten 4 marks for this up here. And let's just see how much marks you receive for. Well, you get 3 marks for finding IS. All right, so now I'm gonna clear some of these things. All right, not yet, not just yet. So they ask the question, the power output of the transformer, given that the voltage of the secondary coil is 55 volts. So what is the power output of the transformer, given that the secondary coil is 55 volts? All right, so here's Johnny. So power, electrical power, is equal to IV. Now the output is going to, so for the output, P out is going to be equal to IS times VS. That means secondary voltage times secondary current. So that is going to be 0.2 ampere times 55 volts. And that is going to be equal to 11 watts. So this W, when you see this W, I mean 11 watts. That's power. Power is measured in watts or joules per second. So here we have that. All right, so this is that answer right there. And you get another 3 marks for that. Wow, they were giving away marks for such things, man. All right, so we're going to one more question. All right, so this question says complete the table by inserting the appropriate physical quantities and derived SI units. All right, so here we go now. If we look at the block down here, they're asking us to find the volume, which is going to be the width times the length times the height. Please note that this is in centimeter while these are in meter. All right? And so we must do something about that. So we're going to change this to centimeter, the centimeter to meter. Remember, 100 centimeter is equivalent to 1 meter. So every time we divide by 100 centimeter, we get how much meter. So just divide this by 100. And as there's 2 zeros, we'll jump the decimal point 2 places and we get 1.4 meter. So this is 1.4 meter, okay? All right. So for the volume here, it's going to be 1.4 times 2 times 3, which is equal to 8.4 meter cube. Cubic meter, because it's meter times meter times meter, or meter right here. 8.4 meter cube. All right? I'm so sorry. They never asked for the volume right here. They asked for the derived SI units. So, pardon my I didn't even read the question. But that we're going to come back to that calculation in any case. All right. So they said physical quantity, derived quantity. Derived SI unit. So this is just meter cube. All right. Length times width. All right. How do we get kilogram per meter cube? That's density. So this is density. As remember that density using the symbol rho is equal to mass per unit volume. All right. How much mass do you stuff in each volume? All right. If we see this symbol here in N, which means Newton, then it must have been force. And pressure can be measured in Pascal, which is PA. Or this is SI unit, so you can't use atmosphere. Atmosphere is not the SI unit. But what you can do now is you can say pressure is mgh. All right? mgh. And what would that give us? Kilogram meter per second squared times meter. So what would this be? Kilogram meter squared per second squared. Or you can say, you remember this formula for pressure? Pressure is equal to force per unit area. All right, so that would be Newton per meter squared. Per meter squared. So scratch this. That's not what we want. Force per unit area. All right, let's clear all of that. You get 5 marks for doing all of that, by the way. The concrete block, it was made of cement. Calculate the density of the block given that the mass is 20,160 kilograms. So please remember that density, rho, is mass per unit volume, which is equal to 20,160 kilogram divided by the volume, which is the 1.4 times 2 times 3 meter cubed. And this is, so this goes 20,160 divided by 8.4. And it's equal to 2,400 Pascal. All right, define the term pressure. All right. So force exerted per unit area on a surface, all right? So let's pressure is the force exerted per unit area on a surface. All right, so the amount of force pressing on a surface and the amount of force and the area of that surface that force is pressing on, right? So the pressure is the force exerted per unit area on a surface. And yeah, so force and area, you have that in mind. Now, given that G is equal to 10 Newton per kilogram, calculate the pressure exerted on the floor by the base of the concrete block. And by saying Newton per, they're given the acceleration due to gravity in terms of, yeah, the amount of force per every kilogram. All right, so if we go back, the base area of this block is going to be the 1.4 times 2. Because those are the dimensions that are touching the ground, right? Which is going to give us 2.8. So what will happen now is that to see the pressure that the block is exerting on the ground, here's how it goes now. So it would be the 20,160 kilogram times the 10 Newton per kilogram. I hope you know that the kilogram and the per kilogram will cancel. Divided by 1.4 times meter squared. And essentially this will equal to 201,600 divided by 2.8. And this is equal to 72,000 Pascal. That's the amount of pressure that that concrete block is pressing on the floor. All right. And we get 4 marks for working that out. And let's see if we can quickly flash through this heat capacity question. Okay, so define the term heat capacity. Now I would want to tell you that heat capacity is measured in joules per Kelvin. So heat capacity is the energy required to raise the temperature of a body by 1 Kelvin or 1 degrees Celsius. So the energy required to raise the temperature of a body by 1 Kelvin or 1 degree Celsius. That is heat capacity. Define the term specific latent heat of vaporization. The energy required to change 1 kilogram of a solid into 1 kilogram of a gas at the same temperature of the solid. So basically that is to say, to change 1 kilogram of a solid into 1 kilogram of a gas without any change in temperature. That means the gas and the solid are at the same temperature when the change takes place. All right? All right, that being said, let's take a look at this next question. It says, a substance which has a freezing point of 80 degrees Celsius was cooled from 90 degrees Celsius to a total solid at its freezing point. Sketch a graph on the figure represent this thing. All right, so let's go sketching now. The freezing point of the substance is 80 degrees Celsius, right? Now let me tell you what occurs at the freezing point. The freezing point is where the latent heat of fusion would operate. And that is where you change from a liquid at a particular temperature to a solid at the same temperature. The temperature will not change at that point. That's where it changes from one state to another. So if it is at 90 degrees Celsius and the freezing point is 80, then what will be happening is that this thing will be cooling down until it reaches 80. When it reaches 80, it is cool enough to start changing into a solid. But while changing into a solid, the temperature does not change for a while. And then when it completes changing into a solid, then it starts to goes down again. This here is the melting point or freezing point. 80 degrees Celsius. As said, it was stated right here. It freezes at 80 degrees Celsius. So at 90 degrees Celsius, it's just cooling down. So the temperature will fall and fall and fall till it reaches its melting point or freezing point. It starts to solidify. While it is solidifying, no temperature change takes place because all the energy that is extracted is given into changing its state. When all the particles are finished changing their state, then it starts to drop in temperature then. Right? So that's what you get. This is what you should get as your cooling curve, and you get 2 marks for that. So I think they need to see they need to see that the temperature stays constant at the melting point for a while, and then it starts to drop, and they need to see it dropping from there for you to get your 2 marks. All right, C now. It says a student conducted an experiment in which 1.5 kilogram of water at 30 degrees Celsius was converted to steam at 100 degrees Celsius. Assuming no heat is lost to the surroundings, calculate the amount of energy needed to heat the water from 30 degrees Celsius to 100 degrees Celsius. All right, let's take a look at that. All right, so here we go now. So we're gonna do that now. Boom. Okay. No, they also give you some figures down here, like the specific heat capacity and so on. So here's how it goes now. The energy, or the thermal energy, or the change in energy that occurs is going to be M little c delta T. M little c delta T. Now, please note that the change in degrees Celsius is also equivalent to the same change in Kelvin temperature. It's just that the exact figures, the absolute figures will not be the same, but the change will be the same. So we can just work this out in, so the mass is 1.5 kilogram. The specific heat capacity, as seen right here, is 4,200 joules for every kilogram. So, you know, it's going to be timed by for every temperature change. And the temperature change is 100 minus 30. All right, so from 30 to 100. Which of course is going to work out to be 70. So when we work this out now, we're going to get 1.5 times 4,200 joules for every Kelvin for every kilogram times a temperature change of 70 degrees Celsius is going to give us 441,000 joules of energy. So assuming no, it is lost to calculate the amount of energy needed to heat the water. This is the amount of energy needed to heat the water from 30 degrees Celsius to 100 degrees Celsius. Now, how much energy would need to convert the water at 100 degrees Celsius to steam at 100 degrees Celsius? So here again, now we have, so the energy is going to be equal to the amount of water, the mass of water, times LV, the latent heat of vaporization, or the specific latent heat of vaporization. So that is going to be equal to 1.5. No temperature needs to be in it because the temperature is not changing, so it doesn't matter. And then we use this big old figure that we see right down here, 2.3. Yes, it takes a lot of energy to change water into steam. Yeah. 10.6, 10 to the 6, sorry, joule per Kelvin, which is going to be working out to, tell you, and this is going to be equal to 3.45 times 10 to the 6 joule of energy. You see how much energy that? 3,450,000 joules of energy is required to change it, the same amount of water from liquid to steam. You see that? And look how the liquid. Anyway, let's keep going. Heat the water. So what's the total amount of energy to heat the water from 30 degrees Celsius to C? Well, we simply add it up. So total energy is equal to 441,000 plus 345,000 dot. And the answer is equal to 3.891 times 10 to the 6 joules of energy. All right. So that's how that would work out. And this is where we're going to stop today. I want to tell you, thank you for your participation. I hope you did enjoy this session, and I hope you did learn something. I hope you realize that physics can truly be easy. It also can be fun. Some of the topics that we did end up looking at today, we looked at some electricity, we looked at dealing with transformers, we took a look at dealing with the gas laws. You know, this is heat, thermodynamics, and so on. So, guys, have fun, look up, hope to see you next time. Where we'll have a longer, more incorporated session. All the best to you, and keep your journey filled with energy as you force your way through to your destination of a 1 in CSEC physics.